strength of materials. Today's topic is deflection of beams. Deflection of beams. So already we studied the beam theory, the assumptions of the beam theory given by Euler Bernoulli. Beam is a long structure which is supported at the ends. Maybe both ends are like one end. That comes under classifications. So when the beam is subjected to complex loads, the beam will undergo bending. Okay. Suppose if I take a long structure, I am taking a cantilever structure which is fixed at one end. Now, when this structure is subjected to transverse load P, we observed that this structure undergoes bending like this, where the top layers will be under stretching, the bottom layers will be under compression. In between, there is a layer which is unaffected. That layer is called neutral layer. Now, from the axis of the beam, so these vertical layers are undergoing displacement in the direction of loading. The displacement in the direction of load is called deflection. At the same time, these cross sections which are vertical before loading, they are vertical before loading, but after loading, these cross sections are undergoing some rotation with respect to the initial position. That rotation is called slope of the beam. Okay. So the deflection is defined as the displacement in the direction of the load. It is the displacement in the direction of load. Whereas slope is the rotation of the cross section. Rotation of the cross section, or you can say section of the beam. Okay. So it is very important to determine the deflection as well as slope for various beams. Because in a structural arrangement, when a structure is subject to loading, the deflection of the slope should not be beyond certain limit. Okay, if they are beyond like a limit prescribed, the structure may undergo failure. So to prevent the failure, we have to restrict the displacement, that is the deflection as well as the slope. So to determine this slopes and deflections for a variety of beams under different loading conditions, there are many methods are there. Most important methods are: 1. Double integration method. So the second one, energy methods. In this energy methods, there are two sub methods again. One is the unit load method. The second one is by Castigliano theorem, or Castigliano's method or theorem, you can say. Then third one, conjugate beam method. Fourth one, moment area method. Like that, there are so many methods are there. Okay, those and even those methods are not much important. Let us discuss the most important and preferred methods in engineering applications. The first one is double integration method. We'll discuss. then we can go for a energy method to find the slopes and deflections. So first, double integration method. The beam theory, when a beam is subjected to transverse loads, if you take a small section at distance equal to x from the free end, suppose this is the beam which is subjected to load. So if you take a small section at distance equal to x from the free end, now this cross section of the beam rotates like this. So at a distance equal to x, here we'll have a small elemental displacement, okay, y. So the moment is given by force into perpendicular distance. M is equal to P into x. Now the bending stress equation which we derived in the previous sessions, that is M by I is equal to E by R is equal to sigma by y. Here M is the bending moment which is because of the transverse load. I is the moment of inertia of the beam, that is I is given by integration of y square into dA. Okay, suppose this is the cross section of the beam. If I take a small elemental area here at distance equal to y from the neutral axis, let the thickness of this is dy. The area of this element, we know dA is equal to y into dy. So that the moment of inertia about this axis of rotation, if this is the x-axis, this becomes Ix. Ix. Okay. Ix. So it's defined as the square of the perpendicular distance times the area gives the moment of inertia, where E is the Young's modulus of the material. E is the Young's modulus of the material, which is the material property. For a given material, E is constant. Then R is the radius of curvature. The radius of curvature is given by, from the mathematical point of view, it is given by d2y by dx square by 1 plus dy by dx whole square to the power of 3 by 2, where y is the displacement or the deflection, x is the distance which we can measure from the free end of the beam. This is the free end. Or we can measure it from the fixed end also. Okay. So generally the slope of the beam will be very small compared to the a deflection. So that's why the slope dy by dx here, if you neglect this one, the approximate equation for the radius of curvature becomes d2y by dx square. This is the radius of curvature equation. Okay. So if I take the first and second terms from the famous bending Flexural equation, that M is given by M is equal to E into I into, that is by R. Okay. Where the product E into I is a constant if the beam is made of the same material and the cross section is uniform. That's why now onwards we can take this as a constant. It is called flexural rigidity. It is the flexural rigidity of the beam. Mostly it will be constant, because if the cross section is constant, material is the same, it will be constant. Now this M, the moment is given by EI into 1 by R. This is the radius of equation, say 1 by R. That 1 by R is given by d2y by dx. d2y by dx square. This is the Flexural equation for deflection, which is given by Euler. Okay. Now in double integration method, we will use this equation. Okay. So let us consider the first case, cantilever beam. subjected to point load. Point load also called as a concentrated load or discrete load. So let us take a structure which is fixed at one end and the load is applied P at the free end. Okay. So this beam, say it's like a rectangular cross section. Okay. We can find the moment of inertia so that E into I is constant here. If I take a section at distance equal to x from the free end, the moment m is given by P into x. Okay. Now apply the equation of flexure. Moment is given by EI into d2y by dx square is equal to P into x. So that d2y by dx square becomes px by EI. If I integrate this first with respect to x, integrate with respect to x, so we will get dy by dx, that is px square by 2ei plus constant of integration c1. So this is the first equation, equation number 1, which gives the slope of the beam. Again, if you integrate with respect to x, we will get y, that is given by p into x cube by 6ei plus c1x plus another constant of integration c2. So where c1, c2 are the constant of integrations which we can determine from the boundary conditions. c1 comma c2 are constants which we can determine from boundary conditions. So here the boundary conditions are, say this is x is equal to 0 at the free end. Here x is equal to L, the length of the beam. So the first condition, when x is equal to L, the first boundary condition, so call this as a second equation. See, at the fixed end, the cross section cannot move down or the cross section cannot rotate. That means the slope dy by dx at x is equal to L will be always 0 for a fixed end. So if you substitute this condition in the equation number 1, that is dy by dx 0 is equal to P L square by 2ei plus c1. From this, we will get the first constant of integration c1 as minus PL square by 2ei. Okay. So the second condition is, see, when x is equal to L, even at the fixed end, the cross section cannot move down. That means the deflection also will be 0. That is, y is equal to 0 when x is equal to L at the fixed end. So if you substitute this in the second equation, that is 0 is equal to, that is PL cube by 6ei. C1 already we know, that is PL square by 2ei into L plus C2, from which we can find C2 as PL cube by 3ei. So we got the constants C1 and C2 from the boundary conditions for a given beam. So that now we substitute back so that we'll have equation for slope. Dy by dx is px square by 2ei minus PL square by 2ei. This is the equation for slope of the beam along the span. Okay. Now here, this equation we can program using any programming language, so that for each value of x, we can plot the slope curve. Similarly, substitute C1, C2 in the second equation, so that we'll get a deflection equation, that y is p x cube by 6ci minus pl square by 2ei into x plus c2 is pl cube by 3ei. So that this is the second equation. So we got the slope and deflection equations for a given structure, cantilever beam. Okay. Now by substituting the value of x at each location, say along the span of the beam, say like when x is equal to 0, we'll get the slope and deflection at the free end. Say when x is equal to L by 2, that means at the center of the beam, we'll get the slope and deflections. And when x is equal to L, we'll get the slope and deflections at the fixed end. Like that, along the span, wherever you want to find the slope and deflections, by using these two equations, okay, we can determine the slopes and deflections. Okay. So now, let us select the maximum values, where the maximum value occurs. For any cantilever structures, definitely, so by observation we can see that, okay, the slope and deflections will be maximum at the free end only. So let us find out the maximum values. So when x is equal to 0, when x is equal to 0, that is theta, the slope tends to theta max, that is dy by dx max. So when x is equal to 0, that means we will get minus pl square by 2ei. So here the negative sign indicates only direction, that's all, nothing else. Okay. This is the maximum slope for the beam, pl square by 2ei, where p is the transverse load, L is the length of the beam, E is the Young's modulus of the beam material, I is the moment of inertia of the given cross section. Okay. Suppose we want to find x is equal to L by 2. That means at the center of the beam, that is dy by dx at x is equal to L by 2. We can substitute back in the equation. Okay. In this equation, we substitute px square by 2a minus pl square by 2a. Here, x is equal to L by 2. If you substitute L by 2, you will get, okay, that is p into L by 2 whole square by 2ei minus pl square by 2ei. So this is L square, 2 means how much it becomes? 4. 4 into 2, 8. Okay. That is minus pl square by 8ei. This is the answer at the center of the beam. Definitely 3 by 8 is actually less than 1 by 2. Then see the deflection. These are the slope equations. Obviously, when x is equal to L, that slope will be 0, because there is a practical condition. Based on the condition only, we got this equation. When x is equal to 0, the deflection y tends to y max. So that is given by pl cube by 3ei. So this is a very important standard formula you have to remember. The maximum deflection for a cantilever beam is given by pl cube by 3ei. So when x is equal to L by 2, the deflection at the center of the beam, that is, if you substitute that, p into L by 2 whole cube by 6ci minus PL square by 2EI into L by 2 plus PL cube by 3EI. You will get 5 PL cube by 48 EI. Okay. This is the value at the center of the beam, the deflection. When x is equal to L, the deflection will be 0. Okay. So this way, since we are integrating the moment equation 2 times, first time integration gives the slope of the beam, the second integration gives the deflection of the beam. That's why it is called double integration method. So in the double integration method, we need to actually identify the boundary conditions. Substituting the boundary conditions, we can get the constants of integration, from which we can have a slope and deflection equations. Then along the span, wherever you want to find the slope and deflections, with respect to displacement, distance, we can find the slopes and deflections. Okay. Now this is for the point load. Like that, the structure can be subjected to uniformly distributed loads or uniformly varying loads, or even moment also. Okay. So a second case I will take for illustration. Suppose, say, this is the cantilever structure which is fixed at one end. Now this is subjected to UDL, uniformly distributed load, where L is the length of the structure. Okay. And EI is always constant. The flexural rigidity of the structure is constant. The load is given by W per unit length. That is the uniformly distributed load. Okay. Here also, now to apply the double integration method, you take a section at distance equal to x. So that when you see the free body diagram of this element here, the load is W or a distance is x. So that the total load becomes area under this element, that is W into x. So now this is a distance equal to x by 2. So this, from this point here, this will try to move down. So there is the upward force F, which will balance the downward load. Now this will try to rotate clockwise. There is a balancing moment in the opposite direction, that is M. So that the moment equation M is force load into perpendicular distance, that is Wx into x by 2. Okay. This is the moment equation. Now apply the Euler equation of deflection, that is Ei into d2y by dx square is equal to wx square by 2. Very similarly, as we did for the previous case, here also integrate 2 times so that we will get the slope and deflections. That is, first integration we will get dy by dx, that is given by wx cube by 6ei plus c1, constant of integration. The second integration gives y, the means deflection, that is given by wx to the power of 4 by 4 into 6, 24ei plus c1x plus c2. Okay. Now substitute the boundary conditions as usual, like when x is equal to like L, when x is equal to L, so we, the slope will be 0 at the fixed end. That is, from which to substitute this value in the above equation, that C1 you will get minus WL cube by 6Ci. Or when x is equal to L, the deflection, that is y is 0. That implies 0 is equal to WL power 4 by 24ei minus WL cube by 6ei plus C2. Okay. From which we can find the C2, constant of integration, WL to the power of 4 by 8 EI. If you evaluate this, you will get this much. Okay. Because into L here. Okay. So substitute back in this slope and deflection equations. You will have the slope equation dy by dx, that is W x cube by 6ci. C1 is WL cube by 6ci. Then the deflection equation, that is Wx to the power of 4 by 24ei minus C1 is WL cube by 6ci into x plus C2 is WL to the power of 4 by 8ei. Okay, these are the slope and deflection equations. We can solve these equations by programming. We can plot the curves, or to find the maximum or minimum values, we can use the boundary conditions. We know when x is equal to 0, the slope will be maximum, dy by dx max. That is given by minus WL cube by 6ci. This is the slope equation. Similarly, deflection equation, when x is equal to 0, that is y max, that is given by WL to the power of 4 by 8ei. In the structural applications, mostly we require the maximum values only, because once you take care of the maximum values, the structure will be safe at the minimum values. Okay. This is y max. Okay. So this way, for a variety of the beams, we can apply this method. We can find the slope and deflections. Okay. Similarly, this you can work out at home. I am giving a structure which is subjected to only moment. Only moment. Okay. Then we have to find the slopes and the deflections. Okay. So apply the moment equation. M is equal to EI into d2y by dx square. M is the moment which is applied at the free end. So therefore, d2y by dx square gives M by EI. If you integrate this twice and substitute the boundary conditions, you will get the maximum slope, that is given by ML by EI. But here we get a negative sign which indicates only direction, and the maximum deflection you will get ML square by 2EI. Okay. You please, students can actually work out this in the similar fashion so that you will get this answer. Okay. Right. Now, let us take a numerical on this. Okay. We have done the like a slope and deflection for a cantilever beam subjected to uniformly distributed loads, moments, as well as point loads. Okay. Of course, one more case is there. That is the fourth case here. The same cantilever structure can be subjected to triangular load, or also called as a uniformly varying load. The load intensity will be 0 at the free end, and it will be maximum at the fixed end. Okay. For this also, you can take the moment equation here. Say, take a section at distance equal to x from the free end. Now, this is the element. Okay. Now, the load. The height of the load here is maximum at a fixed end, and 0 at a free end. So that at distance equal to x, the load height by similar triangles, this height becomes Wx by L. Okay. So what is the total load? The total load is always given by area under the given diagram. So this is a triangle. So for a triangle, what is the load? Half into height into base. Height is Wx by L into the base height is x. So where it will act? The load always acts at the center of the section. So for a triangle, the center of gravity lies at a distance equal to x by 3 from the base or 2x by 3 from the apex. Okay. So this load is Wx square by 2L. So that here we'll have a shear force, Fx will have a bending moment, Mx, to keep the element in equilibrium. So that now our moment equation M is given by load into perpendicular distance. That is Wx square by 2L into x by 3. Now apply the moment equation. That must be equal to EI into d2y by dx square. So now we got the slope d2y by dx square is equal to Wx cube by 6L. Now integrate this first, it will get the slope. Integrate twice, you will get the deflection. Then substitute the boundary conditions where x is equal to 0, x is equal to L at the fixed end. So if you substitute like that, we will get the maximum slope, that is theta max, as W L cube by you please check this. Okay, I think I remembered this, 6 EI. Okay. Whereas the maximum deflection you will get WL to the power of 4 by, okay, this is, sorry, this you will get 24 EI. This you will get WL to the power of 4 by 30 EI. Anyway, these two formulas you can check, because this I roughly remembered these values. Okay. This is the slopes and deflections for a cantilever beam subjected to triangular load or uniformly varying load. The maximum deflection WL cube by 24 EI, whereas the maximum deflection is given by WL to the power of 4 by 30 EI. Okay. So now let us list out the 4 equations which we learned. First, point load. For a point load at free end, the slope is PL square by 2EI. The deflection is PL cube by 3EI. The second one, uniformly distributed load. The maximum slope WL cube by 6EI and maximum deflection WL to the power of 4 by 8EI. The third set, that is, this is a moment. Beam is subjected to pure moment. Pure bending moment. Yeah, okay. The slope is given by ML by EI. Deflection is ml square by 2EA. Then the fourth one, uniformly varying load, that is UVL. Okay. The slope is given by WL cube by 24EI. Deflection is given by WL to the power of 4 by 30EI. You please remember these equations so that we can solve the numericals. Okay. Right. I am taking the problems. The first problem. A cantilever beam of length 2 meters made of rectangular cross section of width, say 40 mm, depth 100 mm, is subjected to a point load of 10 kilonewtons at the free end. The beam is made of steel where the Young's modulus is given as 200 gigapascals. Okay, gigapascals. So the question can be, determine the maximum slope and deflection at the free end. Or anywhere they can ask. Even they can ask the bending stress also. Okay. I'll give the questions. Determine 1. Maximum slope. 2. Maximum deflection. These are the two questions. Okay. Even we can add more questions. Even we can find the slope and deflection at the free end center also here. Even we can find the maximum bending stress, maximum shear stress also. Okay, that comes under like a total design of the structure. Okay, the bending stress calculations, the shear stress calculations we have done in the previous topic. Okay, let us see the solution. First, always keep the given data. What is the given data? Load is given P 10 kilonewtons, right? The Young's modulus is given 200 gigapascals. So you have to convert into megapascals. That becomes into 10 power 3. Megapascal means Newton per mm square. The length is given 2 meters. That is 2000 mm. Okay. Then the I value. I, for rectangular section, we know that I is BD cube by 12, where B is given and D is given. B is equal to 40, D is equal to 100. So, in this, B is 40 mm. The depth of the beam is 100 mm. Okay. Now, what is the formula for slope? Theta is equal to PL square by 2EI. This is the formula we got. Okay. Right. Now, substitute the given values. Okay. That is slope theta max is equal to P 10, convert the kilo into newtons, that is 1000, into L square, that is 2000 whole square, by 2 into E. 2 into this is 2 into 10 power 5. So 10 power 5. 2E I. I is how much? BD cube by 12. B is 40. D is 100 whole cube by 12. The 12 will go to the top. Now, all of you use the calculator and keep the value. The answer will be in radians. Okay. If they ask you to convert it to degrees, multiply the radians into 180 by pi, so that your answer will be in degrees. Okay. So generally, the thumb rule of the structural design is the slope should not exceed 1 degree for a safe design. That's one kind of thumb rule. Okay. You see how much like a slope you will get. Definitely that will be less than 1 degree only. Okay. Then only we can say the structure is reliable and safe. Then the second. Okay, this is the first one, slope. The second one is deflection. What is the formula for deflection? PL cube by 3EI. Okay. So, P is given 10 into 1000, L 2000 meters cube by 3 into E 2 into 10 power 5 into I B cube by 12. B is 40 into D whole cube by 12. So that your answer will be in mm. Okay. The deflections will be very small, so that we will measure in a small unit like a mms. Okay. So this way we can find the slope and deflections. So these are the maximum values. Okay. Generally, the deflections will be like depends on the length of the structure and size of the structure. So they vary from like a 1 mm to up to 5 mm. Even in some cases, even 10 mm deflection also may be permissible. That depends upon the structural alignments. So you can copy this. All of you use the calculator, find the slope and the deflections, and keep the values. Okay. From the given values, you can actually see the physical meaning of the like loading, how it will deflect, and what is the magnitude of the deflection, what is the magnitude of the slope in degrees, and we can say whether the structure is safe or not. Okay. Or the values are within permissible limit or not. Okay. Second question. Okay. See, sometimes this is the structure, okay, cantilever structure. Now the load will be applied here at distance equal to L by 2. That is, at the center of the beam, the load is applied. Okay, this beam length is L. Okay, this beam length is L, and it is made of material strength E and cross sectional is I, so that EA is always constant. Now the question is, what is the maximum slope and deflection for this beam? Say this is the A fixed end, B where the load is applied, C the free end. There are 3 points are there. Fixed end A, the point where the load is applied at the center of the beam B, and C is the point at the free end. Now the question is, what is the maximum slope and deflection? What is maximum slope and deflection is the question. Okay. Now whenever you apply load here at the center, from B to C, it is like a overhang portion. There is no load. Where there is no load, the slope remains constant. Remember. Okay. Note. Okay. For a cantilever structure, from the free end, okay, if the load is acting somewhere, from the point of loading to the free end, there is no bending. When there is no bending, the slope remains constant. So, this structure, okay, when you apply load here, P, so this structure will deflect like this. And from here, it will go straight. Okay, it will go straight like this. So that here we'll have some slope. And this is the slope here. Suppose this is the slope here is theta C. The slope here is theta B. So that implies theta C will be equal to theta B. Because from B to C, no bending. Remember. From B to C, no bending occurs. Okay. So that it will go straight. Now, at this point, here we'll have a deflection. This is the deflection at point B. That is YB. The length is how much? L by 2. So that the deflection is given by P into length is L by 2 whole cube by 3 EI. That implies PL cube by 24 EI. This is the deflection at B point. Then what is the slope at B point? The slope at B point is given by P L square, but length is how much? L by 2 only. P L by 2 whole square by 2 EI. That is P L square by 8 EI. So we got the slope on deflection at point B. Now see, if I draw a horizontal line here, okay, this distance becomes YB. So this distance, okay, see, this is theta C. If I drop a line, see closely, if this is theta B, this line and this line are perpendicular, so that this angle becomes 90 minus theta B. Again, this line and this line are perpendicular, so that if this is 90 minus theta B, this becomes theta B. So that to apply the formula, S is equal to the arc. This distance becomes a kind of like a arc only. That arc is given by arc is equal to length into the angle. This length is L by 2 because L is the total length of the structure. So that this becomes theta B into L by 2. Now what is the total deflection at C point? From here to here, that is YB plus theta B into L by 2. So therefore the YC, deflection at C point, is equal to deflection at B point plus slope into L by 2. So substitute the YB value, that is PL cube by 24 EI plus theta B is PL square by 8 EI into L by 2. So that the YC, deflection at C point, if you evaluate that, you will get 5 by 48 PL cube by EI. This is the answer. Anyway, theta C, I told already, it's like a theta B only. How much you'll get? P L square by 8EI. These are the answers. Okay. This is second question. Like that, the load can be applied anywhere. Next time they may ask you a distance equal to L by 4 or L by 3. Okay. Whatever may be that. Okay, you follow the same procedure. From the point of fixing to the point where the load is applied, up to that point, you will have bending. From that point to the free end, there is no bending. When there is no bending, in that portion, the slope will be constant. Okay, you have to remember that. Then you can apply the simple mathematical equations from the already derived formulas. You will get the answers. Okay. Right. Third question. Okay. Suppose if the beam is subjected to complex loading, that means combination of the loads. Say here, this is the cantilever structure. Okay. Cantilever structure. It is subjected to a point load followed by moment. Like that, the structure can be subjected to any number of loads. Of course, we can even add UDL also. This is called compound loads. Means combination of like a more than one load. So it's a point load, is a moment, and then this is UDL. Where L is the length of the beam, EA is the constant for the beam. Now, if all are in the same direction, at any point, the slope and deflections we can add or subtract. Okay, based upon the method of superposition. For this kind of things, if you want to find the maximum values, this is a combination of point load plus moment plus UDL. Okay. So, if the directions are suppose different, suppose the load is applied upward, you can use the proper sign convention. Okay. Now, all the three loads are clockwise, all are positive. Say this is 1, 2, 3. So that this will undergo bending like this. This also undergoes bending like this. This also undergoes bending like this. So here the slope theta 1, deflection y1. Here the slope theta 2, deflection y2. Here the slope theta 3, deflection y3. Okay. Since all the loads are in the same direction and the loads are applied within elastic limit. Of course, all the structural designs we are doing within elastic limit only. So that now the method of superposition states that when the structure is subjected to compound loads, the slopes, deflections, bending stresses can be added or subtracted at a particular location with a proper sign convention. Okay. That means if this is the structure, the resultant slope is theta and the deflection is y, the slope theta is given by theta 1 plus theta 2 plus theta 3. This is the resultant slope. So with respect to values, already we know the formulas. This is PL square by 2EI plus this is M L by EI plus this is WL cube by 6 EI. Okay. Similarly, the deflection is given by y1 plus y2 plus y3. That is PL cube by 3EI plus ML square by 2EI plus WL power 4 by 8EI. Okay, this way. If you change the direction of the load, you can use the proper sign curve. Okay, suppose the load is acting upward, it will be minus. The load is acting down, plus this way. This is the method of superposition. Even suppose you take a point here, the bending stress sigma is given by sigma 1 plus sigma 2 plus sigma 3. This way. So this way, when the structure is subjected to complex loads, we can find the resultant slope and deflections by the method of superposition.
Like, share and subscribe. Hit the bell icon for more updates.